In this demonstration, we begin by applying a high-pass Butterworth filter to a PPG signal using Matlab. First, the signal is loaded from a CSV file and plotted. The sampling frequency and cutoff frequency are defined, and the cutoff is normalized using the Nyquist frequency. A Butterworth filter is then designed, and zero-phase filtering is applied using the filt-filt function. This method ensures the signal is filtered in both forward and reverse directions, eliminating any phase distortion. The output is compared with the original signal to observe the drift removal and preservation of high-frequency components. After Matlab filtering, the PPG signal undergoes pre-processing for Simulink. The signal is truncated or zero-padded to 1250 samples and then converted into fixed-point format with 24-bit word length and 20-bit fraction length, suitable for FPGA processing. The data is then converted back to double precision and structured as a time series object, which is passed to Simulink using the From Workspace block. These pre-processing steps make the signal compatible for HDL code generation in the next phases of the workflow. Continuing from the pre-processing step, we now move into Simulink model creation. First, a blank model is opened in Simulink. We start by adding a From Workspace block. This block allows us to import signal data directly from Matlab's workspace into the Simulink environment, which is essential for feeding pre-processed or experimental data into our model. After placing the block, we configure its parameters. Here, we make sure the signal name matches the variable available in the workspace and adjust the sample time accordingly for proper simulation synchronization. Next, we introduce a data type conversion block. This block ensures the input data is transformed to the format required by downstream operations, which is especially important for HDL compatibility and numeric precision in fixed-point designs. We adjust the output data type settings here based on the target application. Following that, we integrate a Matlab function block. This is where we can write custom logic using Matlab code. It enables algorithmic control, complex conditions, or calculations that are otherwise cumbersome with graphical blocks. Inside this block, we define the core functionality of our system. After executing the Matlab function, we use a to-workspace block. This block sends the output signal from the Simulink model back into Matlab's workspace. It is vital for post-simulation analysis, allowing us to visualize results, run custom plots, or we continue the model development by adding scope blocks to monitor signal behavior in real time. These are connected at key points in the signal flow, such as after the Matlab function, to validate output visually during simulation. With the scopes in place, we double-click to open the Matlab function block. Inside, we begin defining a custom function using Matlab code. This function performs specific operations on the input signal, such as filtering, thresholding, or conditional processing, depending on the requirements of our model. After completing the logic, we save and close the function editor, committing the script into the block. Returning to the Simulink canvas, we verify all connections and finalize the design. To preserve all changes, we save the Simulink model, ensuring the block structure, parameter settings, and custom code are ready for simulation and reuse. We begin by selecting a group of blocks in our Simulink model. These blocks together form a logical unit, which we will now encapsulate into a subsystem. By right-clicking and selecting Create Subsystem from Selection, Simulink automatically wraps the selected blocks into a single modular block. This helps simplify our top-level diagram and improves readability. Now, we double-click to open the newly created subsystem. Inside, We can see all the internal connections remain intact, making this an effective way to encapsulate functionality. After confirming the structure, we return to the main model and run the simulation. This compiles the system and starts executing based on the configured simulation parameters. The scope block now shows the resulting plots, allowing us to visually analyze the system's output and verify that the behavior matches our expectations.